We're going to take a look at how these covalent bonds actually form. All right, so last week we looked at ionic compounds where there was the transfer of electrons from the metal to the non-metal. Now we're going to see how electrons are going to be shared between nonmetals. So again, molecular or covalent compounds form when nonmetals share electrons. Right, so again, to reiterate this, if your covalent compounds and your covalent bonds, we're going to have nonmetals only, right? They're different from your ionic compounds. And then electrons are being shared, also a big difference from your ionic compounds. And we, in the previous section, we looked at the naming system being different as well. So let's take a look at how these covalent compounds and covalent bonds can actually form in the first place. Now, do you remember last week when we said that, or we tried to come up with the reason why a metal will want to lose electrons or why a non-metal would want to gain electrons in the first place? What was the reason for that? Because they were unstable, right? So they wanted to be more stable. And from what we talked about in class on Monday, which elements on the periodic table are stable? The noble gases, right? On the right side, in group 8, right? Those are the noble or the inert gases. So when you're in your ionic compounds, when your metals lost electrons or when your nonmetals gained electrons, they tried to have the same number of valence electrons, right? Electrons in their outermost shell, as the nearest noble gas. And they could do that by either losing electrons for the metals or gaining electrons for the nonmetals. Now we're going to see, this is going to be another way by which your nonmetals specifically are going to become more stable. They're going to share electrons so that they have the same number of valence electrons as the nearest noble gas. All right, so let's write that down. So electrons will be shared so that each atom has the same number of valence electrons as the nearest noble gas. All right, that's what we're going to use to predict how these things are going to come together and get stuck together with these covalent bonds. So let's take a look at the simplest example of a covalent bond, which is what forms when we have hydrogen. So hydrogen, if you remember, is in group 1 of the periodic table. How many valence electrons does hydrogen have if it's in group 1? So we can draw the Lewis structure for hydrogen. That looks like that. What's the nearest noble gas to hydrogen? Helium. Helium is over on the right side. How many electrons are in helium? 2, right? And that's all the electrons that it has. So hydrogen has 1 electron. Helium, the nearest noble gas, has 2 valence electrons. So in order to be like helium, hydrogen needs 1 more. Everybody follow? So if I have another hydrogen over here with its 1 valence electron, can they help each other out? Yeah, they can share that pair of electrons between them. So now this H here on the left side, because it's now sharing, it has 2, and the one on the right, because it's sharing, has 2 as well. So by sharing a pair of electrons, both of those H's now are happier than they were individually. So we call this a covalent bond. That's the glue that sticks those 2 H's together. We can represent this a little more concisely as a single line. Right? And when you see that single line between 2 things, this always means 2 electrons are being shared. So a single line is called a single covalent bond. Right, and by sharing those 2 electrons, both of those H's now are happier than they were individually. So that means when we make that molecule, how many H's do we have in a hydrogen molecule? 2 H's, right? So the formula for hydrogen is H2. Under normal conditions, hydrogen is going to exist as H2 because it is more stable in that form than if an H were by itself, if we had 2 H's by themselves. Does that make sense? Okay, the driving force here is that these things want to be more stable, and the stablest things on the periodic table are over on the right side, the noble gases. So in terms of electrons, specifically the valence electrons, this is a way in which your nonmetals can become more stable by sharing those electrons. All right, so what we just came up with there is an example of a Lewis structure. In this case, for the simplest molecule there is, which is hydrogen, right? So this here would be the Lewis structure for H2. And as you probably realize, in order to draw the Lewis structure, we need to first of all start off with the Lewis symbol, right, for H, which had 1 valence electron in it. So let's take a look at a couple other examples where we can form these covalent bonds. So let's take a look at fluorine. Fluorine is in group 7. So how many valence electrons in F? 7. Nearest noble gas to F, if you have a table with you. Neon, Ne. How many valence electrons in neon? 8. Fluorine right now has 7. It needs 1 more. So if there's another fluorine floating around with its 7 valence electrons, can they help each other out? No? Yes? Somebody said they can, right? If this fluorine on the left now, 1, 2, 3, 4, 5, 6, 7, shares 1 electron from the other fluorine, then it's going to have 8. And it's going to be happier. And then if they're sharing that, well, then the one on the right is going to have its extra 1 to give it 8 as well. Right? So we're going to have a bond forming between those 2 F's. So we can clean up our structure a little bit and we can draw it like this. So we have the F connected to the other F by that bond, that single covalent bond. Which again means 2 electrons are being shared. Right, but we also have those electrons on the outside of each of the fluorines to make sure that they have a total of 8. Right, so we need to include those. We'll draw those in red. And we refer to those electrons that are not involved in bonding. We call these non-bonding electrons, also referred to as lone pairs, because they come in 2s and they're by themselves. Right? So each of the F's here is going to have a total of 8, sharing 2 and then 3 lone pairs. So what's the formula for the fluorine molecule? It's F2. Right? We can do something similar with oxygen. Oxygen is in group 6. So it's got 6 valence electrons. It wants to have 8, like neon, the nearest noble gas. So if I have another oxygen over here with its 6 valence electrons, they each need 2 more. Right? So they can share 2 pairs of electrons between them. That looks like that. So if I were to draw my structure more concisely, right, it would look like an O connected to another O. And what's the glue holding them together now? What would that be? There'll be two lines. Two lines between them, right? Where each line represents two electrons, right? So two electrons here, two electrons here. So if a single line was called a single covalent bond, what would two lines be called? A double covalent bond. And how many electrons are shared in a double bond? 4 electrons, right? You have 2 for each of the lines. So 4 electrons are shared, right? And don't forget that you still have your lone pairs left on each of those O's, and you have to include those. So that's the Lewis structure for oxygen, which is what you're breathing in right now, and the formula is O2. Right, having 2 O's linked together is way more stable than having a single oxygen. All right, we can go through. I'll just give you the end result of nitrogen. So nitrogen is going to look like this. So I have an N connected by 3 lines to that N over here. If I look at the nitrogen on the left, how many electrons are around it? Remember, each line represents 2, right? So 2, 4, 6, 8. And then the one on the right also has 2, 4, 6, 8 electrons, right? So they're both happier than they were individually. What would this type of bond be called? 3 lines would be a triple bond. And how many electrons are in a triple bond? 6 electrons are going to be shared, right? So that means nitrogen is going to be more stable when it's in the form of N2. That actually makes up about 78% of the air that you're breathing in right now. Every breath you take, right, has a bunch of N2 in it, nitrogen. It's not N, it's N2. So when you go through the periodic table, right, what you'll see is that there are several of the elements that occur naturally as diatomic molecules, right? And we've gone through and we've shown you several examples of these. So these are going to be diatomic molecules, meaning that they're made up of 2 atoms. And there are 7 of them. And where they're located on the periodic table actually gives you an indication of how to locate, how to find them, right? So nitrogen, oxygen, fluorine, which are the ones we just did, along with a few of the other halogens, chlorine, bromine, and iodine, and then hydrogen way over on the other side. Those are the 7 that exist under normal conditions as diatomic molecules. If you sort of outline where they're located, what does that look like? What number does that look like? It's like a 7, right? So they form a little corner there on the right side of the table, and then the H is kind of out by itself on the other side. Right? So those 7 elements exist as diatomic molecules. All right, so we've seen examples of relatively simple Lewis structures. Now we're going to take a look briefly at how we draw more complex Lewis structures. And when it comes to having more than 2 elements in or atoms in a molecule, we're going to have to use some steps that are logical and that are going to make sense as we go through the process. So when it comes to drawing Lewis structures, the first thing that you want to do is to count the total number of valence electrons. So for example, if we look at methane, CH4, how many valence electrons total will we have in methane? So how many valence electrons in carbon? 4. Carbon's in group 4. And we have 1 carbon in our formula, right? So 1 times carbon would give us 4 valence electrons. We also have hydrogen. Hydrogen is in group 1, and we have 4 of them. So that would give a total of 8 valence electrons, right? So we count how many electrons we're going to be working with in our structure. So when we draw our structure at the end, we know that it should have 8 electrons in it. All right, the next step would be to arrange the atoms in a way that makes sense. And this only comes with practice. You get a lot of practice in lab today, and you had some practice in lab on Monday, those of you that had lab on Monday. I have carbon and 4 H's. We need to decide what goes in the middle, first of all. Monday lab people, what are you going to stick in the middle? Carbon, right? You see carbon in a structure, put it in the middle right away. And then we have 4 H's. Where do you think those H's are going to go? If C is in the middle, the only place for the other H's to go would be around it. Right? So we can put them in, line them up all the way around. Then we connect the atoms. With a bond, which is just a line. So we connect them all, so the atoms don't float away, right? Because this is a molecule, these atoms are all stuck together. And then we check how many electrons are in our structure right now. 2, 4, 6, 8. And that's how many electrons we were working with, right? So we can't add any more electrons to this. We also need to confirm that each of our elements are happy. Are the H's good? Right? Each H is sharing how many electrons? 2, and that's how much it wants to have, right? So all the H's are fine. What about the carbon in the middle? How many does it want to have? 8. How many electrons is it sharing? 8. So the carbon's good, H's are good. We have 8 electrons in our structure. That's our Lewis structure for CH4, or methane. Right? Those are the steps that you want to follow when you start drawing Lewis structures for your molecules, right? Whether they're simple things or even when they're complex molecules. All right, let's take a look at another example where we can encounter a Lewis structure that has multiple bonds in it. All right, so let's take a look at CO2 carbon dioxide. So we said the first thing we want to do is to count the number of valence electrons. We have 1 carbon and we have 2 oxygens. So carbon's in group 4, so it's got 4 for the 1C. Then oxygen is in group 6. We have 2 O's, so 6 times 2 is 12. So 12 plus 4 is 16 valence electrons. So when I draw my structure, I should have 16 electrons total in it. We're establishing that at the beginning, so at the end we can check to make sure that the structure makes sense. All right, next step, arrange the atoms. We have C and 2 O's. What do you think goes in the middle? We put the C in the middle, and then our O's are going to be on the outside. The next step was to connect them, right? So we connect them with a bond. So in this case, what we're going to do, and in all cases actually, we start on the outside and work our way in. So start on the outside, give the outside atoms enough electrons so that they have how many that they need to have. So how many electrons does the O need to have total around it? Total, how many? 8. Right now, how many does it have? 2. So it needs 6 more. We can put those 6 right around that oxygen, like that. So those are our 6 electrons put in as lone pairs around that O. We can do the same thing for the O on the other side, right? We're dealing with the outside atoms first. And the O on the right side is in the same boat. It's in the same situation. It needs 6 more. All right, then we pause. We count. 2, 4, 6, 8, 10, 12, 14, 16. Those are my 16 electrons. The O's are good on the outside. Is the C in the middle happy? No. How many electrons does it have right now? 4. How many more does it need? It needs 4 more. So I can't add any more electrons to this. The way that we address that problem with the C is we can move pairs of electrons around. And specifically, we can take one pair and move it in to make a double bond between the C and that O. So the C is a little bit happier now, but it's not completely happy. Still needs 2 more. And on the left side, I can do the same thing, right? I can take a pair of electrons and move it in to make another double bond on the other side between the C and that O. All right, so now the carbon has 2, 4, 6, 8. It's good. The O still has its 8, and the O on the left also has 8. So everything's happy. We have our 16 total electrons. That would be our Lewis dot structure for carbon dioxide, CO2. So you're going to get a lot of practice in lab today, those of you that have lab this afternoon. This is a molecule that you did, the Monday lab people, you did that one in lab. So when you start going through the elements, what you're going to see is that in the majority of cases, the atoms want to have 8 electrons around them, right? And that's called the octet rule. All right, so the octet rule, the atoms want to have 8 electrons around them. There are a few exceptions to the octet rule. We already addressed one of them. Hydrogen only needs 2. It can only form 1 bond. And then when we get to some of the elements lower down in the periodic table, so for instance, period 3, so the nonmetals in period 3 and below, right, those are also going to be exceptions. They actually can accommodate more than 8, all right? We're not going to deal with those in this class. We'll save that for later on. But we are going to see hydrogen a lot. So it's important that you know hydrogen can only form 1 bond. It only needs 2 electrons to be happy, right? Because the nearest noble gas to hydrogen is helium, which has